Here's a slightly trickier one. Part A. You have the n numbers 1, 2, and so on n written on a blackboard for some given n. In one move, you can erase two numbers a and b and write the number a plus b on the blackboard instead. You keep making these moves until only one number remains. So first of all, prove that this will happen after precisely n-1 moves. And then the actual question, will the remaining number depend on the moves, on the specific moves you have taken? You have several options. You can begin with 1 and 2, for example, or you can begin with 1 and 3. It's a decision, and you have many more decisions in the process. And if it won't, what is this number? Part B is same question, but instead of actually questions, but instead of a plus b, use a minus b. Part C, same questions, but use the product instead of the sum. Part D, use a plus b plus 5 instead of the sum. Part E, use ab plus a plus b instead of the sum. Basically, you can write any expression with a and b in there, and you can play around with it. It's kind of fun. Just one more, a square plus b square. Okay, so what would you do? First of all, why is it always going to be n-1 moves until only one number remains? This is a question about a monovariant, but it's so easy as that I will solve it here. So each move decreases the number of numbers on the blackboard by precisely 1. Thus, after n-1 moves, there will be exactly one number left. And so this whole only one number remains state is reached after exactly n-1 moves. Fewer moves and you will still have more numbers, whereas more moves it's impossible because you cannot do a move with only one number left. Okay, so this part is done. Now what's left is this question. These are the interesting ones. So let's do this with n equals 4. You have 1, 2, 3, 4. Let's say you pick the 2 and the 4 and you replace them by 2 plus 4. So now instead of 2 and 4, you have 6. Now let's take the 3 and the 6 and replace them by 3 plus 6. This is 9. 1 and 9 become 10. Alternatively, of course, you could have done it in another way. 2 and 3 make 5. 5 and 1 make 6. 6 and 4 make 10. And now this should not be very surprising. Part A is really a warm-up for the other parts. So what's going on? The claim is that the remaining number will not depend on the moves. It will always be the sum of all the numbers. Proof? There is an invariant. The sum of all numbers on the blackboard stays the same because replacing a and b with a plus b, so I take out two addends, and in each move I take out two addends from the sum, and I introduce this new addend, which is their sum. Does not change the sum. So at the beginning, the sum was 1 plus 2 plus and so on plus n. Hence, at the end, it will still be this. But at the end, there is only one number left. So if that one number is this, then of course, if the sum of that one number is this, well, that one number must be this. So this is why we know that it's always 1 plus 2 plus and so on plus n. Part B, The difference one, well, you cannot easily find such an invariant, and it doesn't exist because the answer is no. The remaining number will depend on the moves. This is visible even for n equals 2, because starting with 1 and the 2, you can make either 1 minus 2 or 2 minus 1, depending on which one you choose as A and which one you choose as B. But these are not the same, of course. So, and you can make such examples for bigger n's. It's not just 1 and 2. Okay, what about AB? Well, AB, this is saying the sum is replaced by a product, and we can basically do the same thing with the product sign. And what do we do with the proof? The same thing. The product is now, instead of the sum, you have the product. Okay, now more interesting maybe, A plus B plus 5. The sum does not stay invariant. When you replace A and B by A plus B plus 5, the sum increases by 5. The product also changes. However, I claim that the remaining number will still not depend on the moves. If you want to have a break for thinking, this is a good place for it. But now let me go on with the solution. I define the weird sum of k numbers a1 up to ak to be the following sum: a1 plus 5 plus a2 plus 5 plus and so on plus ak plus 5. You can also say that it's the sum of them all plus 5k, but we don't care. This is what we need. Now, the weird sum of all numbers on the blackboard is an invariant. It does not change. It stays the same. Why? So what happens here with the weird sum when I make a move? I replace a plus 5 and b plus 5 by a plus b plus 5. Sorry, a plus b plus 5 plus 5. So why? Because I had a and b and I replace them by a plus b plus 5. But in the weird sum, I'm adding 5 to each addend. So in the weird sum, I have a plus 5 and b plus 5. And now I throw them away and I get a plus b plus 5 plus 5. And of course, this is just this plus this. So it does not change the weird sum. And now it's just a matter of computing what it was. So at the beginning, this weird sum was 1 plus 5 plus 2 plus 5 plus and so on plus n plus 5. This is 1 plus 2 plus and so on plus n plus 5n. Hence, at the end, it will still be this here. Okay, so now we know what the sum will be at the end, except, do you see what's going wrong here? Minus 5. The thing is, this is going to be the weird sum of the one number that's left at the end. But the weird sum of a single number is a single number plus 5. So if you want to know the number, you have to subtract 5 from the weird sum. And that's going to be the answer. Now, part E, I claim that again, the remaining number will not depend on the moves. So what will it be? And again, you can stop here if you want to think about it. Let me move on with the answer. The invariant now, I'm going to call it the weird product. Define the weird product of k numbers to be a1 plus 1, a2 plus 1, and so on, ak plus 1. So I multiply them, but first I add 1 to each of them, and only then I multiply. Now I claim that the weird product of all numbers on the blackboard does not change. Why? So what happens when I make a move? I have two factors that are a plus 1 and b plus 1. I throw them away, and what I get instead is I take this thing here and add 1 to that. And I claim that this does not change the weird product. Why not? Because this is precisely what you get if you multiply a plus 1 by b plus 1. Just expanded it, you're going to see. So all I've done is I've consolidated two factors into one. Okay, and now what was the weird product at the beginning? It was 1 plus 1, 2 plus 1, and so on, n plus 1, which, by the way, is n factorial if you're interested, because this is 2, this is 3, this is, and so on, and you can add a 1 factor. Multiplying by 1 doesn't change anything. But anyway, let me erase this again to make this clear how this is coming from. So at the end, the weird product will still be n plus 1 factorial. So what will the remaining number be? The weird product of the remaining number will be n plus 1 factorial. But the weird product of a number is that number plus 1. So to get the number, I need to subtract the 1 out. And that's your answer. And you can think of similar problems, but let me actually finish it. Let me do part F. I claim that, again, the remaining product is dependent on the moves. So you won't find an invariant, nor should you be looking for one, because there is no such answer. It's going to depend on the move. You don't see it for n equals 2 because addition is commutative. But for n equals 3, already you see it. Starting with 1, 2, 3, you can make either 1 square plus 2 square plus 3 square square, or 1 square plus 2 square square plus 3 square. These are the two ways you can make this algorithm. And then, no, actually there is a third way, but these two results are already different. And the third way is 1 square plus 3 square plus 2 square. You don't have to take, sorry, square. You're not required to take two consecutive numbers. So, and this is, I'm pretty sure this is something yet different. Yes, 104. So play around with it, invent other rules. Sometimes you will find invariants, sometimes you will not.